I welcome you all for another session. I shall continue the discussion on undamped free vibrations. The basic aim of study of this topic is to know what is the natural frequency of the system. The kind of systems what we discuss in this for this purpose happen to be only single degree of freedom systems. We can think of infinite number of single degree of freedom systems, which few of them I shall be demonstrating you and pick those systems and find what is the natural frequency of the system. We start with a very simple ones and then gradually we shall increase the complexity. So yesterday I took the simple spring mass system, and using the Newton's second law I wrote down this equation which is called as differential equation of motion, and then based on this or looking at this I wrote down the expression for what is called as the natural frequency of the system. Okay, I employed Newton's law, Newton's second law I made use. Okay, I shall take one more system and the next one what is called as simple pendulum. Again I shall employ Newton's second law, and then I shall show you how I can write the equation of motion, differential equation of motion, and from that how I can write the expression for natural frequency. That's what I shall demonstrate. Okay, these two systems I shall carry on, and then for these two systems I shall employ what is called as D'Alembert's principle and write out the equation of motion and the natural frequency. That's what I shall obtain that. Then I shall continue that and then take up energy method, and then also what is called as Rayleigh's method. Like that, all those methods I shall introduce you. Once we understand the method, then it is left to us. So when a system is given, then which method to apply, okay, it is left to us. You can choose any one of them and apply, and ultimate aim is to get what is called as the natural frequency of the system. That's what. So which method you apply, okay, normally we don't, it doesn't matter. But usually in the examination, they normally, whenever they want to ask the energy method, they will clearly mention, do this by energy method. So otherwise the other methods are not employed, and based on our experience when we go on solving the problems, you will also understand which method to employ. So Newton's second law or D'Alembert's principle, both of them are almost one and the same and very simple ones. Okay, as you will come to know as and when we take up the problems. So it is a simple pendulum. Okay, so any simple pendulum. What is pendulum? Pendulum is basically a mass which is going to oscillate. That is called as pendulum. Okay, if the mass happen to be a point mass, then we call it as simple pendulum. Remember, we also have something what is called as compound pendulum. Compound pendulum is also something which is suspended about some point and the whole body is going to oscillate, and the body is not having a point mass, the body's mass is distributed. That we call it as compound pendulum. Okay, so pendulum is basically something which is going to oscillate. So here O is the point, I shall call this as O. O is the point about which it is going to oscillate. See what I have here, I have a point mass. Intentionally a small spherical shaped ball has been taken to represent the point mass. That point mass has been attached with a thread, okay, thread whose mass is negligible, and this length. So the distance between the length of the thread, okay, from the point of suspension to the center of the ball, that is normally called as the length of the pendulum. That I shall indicate it by L. So the mass, this is the point mass whose mass is here. Okay, so right now forget this. Look at the O is this vertical line and this ball, and this position I say that it is the equilibrium position. That is the position where the ball is not moving. Okay, now I induce the free vibrations. How I can do it? So I take this ball and bring it. Please make sure that this is being done in the same plane. I don't pull this ball something like this. So take the ball and in the same plane move it such that the thread is always under tension. Okay, the thread is not collapsed. Okay, bring it here and probably leave it. So when I leave it, this ball will go on moving like this. A very common thing what you have seen it. When maybe in your school days also you are studying this simple pendulum. Okay, this is going to oscillate. So what are the kind of vibrations? These are free vibrations, because when these vibrations are taking place, you have not applied any force. Only for the sake of starting, probably you have pulled it here and brought it and released it. So when the vibrations are taking place, there is no external excitation, and therefore these vibrations are free vibrations. And I presume that we assume that there is no damping, there is no friction, or there is no air which is opposing this motion. Probably you have to have very ideal conditions so that there is no air in between, or it is in vacuum. So there is no air resistance, there is no other kind of resistance, friction, and therefore I say that the system is undamped. Okay, the system is undamped, the vibrations are free vibrations, therefore it is a case of undamped free vibrations. Then what about the degree of freedom of this? So I know that if the ball is in this position, okay, how many variables do I need? If I just know one variable, what is called as theta, say 30 degrees. Okay, one variable. See, if I say that if it is this side, I take the positive angle, and if it is this side, say minus. Okay, if it is 30 degrees, probably this. If it is 35 degrees, maybe somewhere here. If it is 10 degrees, you can easily look at. If it is minus 5 degrees, then it is this side, measure minus 5 degrees, and you know what is here, and you can draw the ball there. What I mean is, with only one coordinate, it is sufficient for us to locate the system at any time, and therefore its degree of freedom is only one. Therefore, it is 1 degree freedom system, it is undamped vibrations, it is free vibrations. Okay, now I have started the vibrations. I have pulled it here and left it, and it is what is going on. Now I want to identify. So this C is the position at some time. Say let me call it as t equal to t. This is the position at t equal to 0. This is t equal to 0, and it is going on. It has made observations, and I observe what is happening at t equal to t. So I take a camera like that. I arrest in my eyes. I arrest this position. Okay, I arrest this position. Okay, then I shall draw the free body diagram of that mass. Okay, this is the mass, this is the position. So I know that its weight is acting vertically downwards. Probably this is the mg. And what is this? This is the thread. This is the thread. Okay, and it goes like this. And if I cut the thread, then I have what is called as the tension in the thread. Please remember, this will go, and this is the point O, and this angle is what is theta. Okay, so coming back to this diagram, I know that this has undergone a displacement of theta. When I say displacement of theta, naturally it is angular displacement. So these vibrations are angular vibrations. And I know that this ball in this position is not stationary, it is having the velocity, it is having the acceleration theta double dot, and all of them I take positive in this direction. If it is like this, then I take it negative. So similarly here, this angle is theta. Okay, and I know that it is having an acceleration of theta double dot. So is there any other force? I don't have a spring here. I have a string which itself acts like that. Okay, this is the tension in the string. This is the weight of the ball, and this makes an angle theta. And if I draw it here, and this angle also is equal to theta. Okay, all I have drawn. This diagram is very important. This diagram is called as free body diagram. Free body diagram at t equal to t. Okay, now what I do? I apply Newton's second law. So what is the Newton's second law? Please remember what is the kind of motion? The kind of motion is angular motion. Angular motion. So what is Newton's second law for angular motion? This is equal to, this is what I have written, M is equal to I into alpha. What is M? The sum of the moments. The sum of the moments, SUM. Sum of the moments due to all the forces. Due to all the forces about what? About the point about which the rotation is taking place. And in the direction of angular acceleration. Okay, how many forces do I have here? One is mg, the second one is tension T. These are the only two forces I have. So I need to find out the moments due to these forces, and if that moment is in the direction of theta double dot is my angular acceleration, and in that case that moment is taken as positive. If that moment is opposite to theta double dot, then I take it as negative. Okay, I hope you understand. What is this here? Sum of the moments due to all the forces about a point about which the rotation is taking place in the direction of angular acceleration. That is very, very important. Okay, so now I have two forces. One is mg, the other one is t. Let me start with this t, the moment due to t about O. O is the point about which the rotation is taking place. This t passes through O only, and therefore it shall not have any moment. So you know moment, what is moment? Moment of a force about any point. The force multiplied by the perpendicular distance. So here the perpendicular distance is 0 because that force is passing through O only, and therefore it will not have any moment. And now you are left with only this mg. Okay, the moment due to this mg about O. So before you proceed, what is this theta double dot? This is my positive theta double dot about O, and this direction, what is this direction? Anti-clockwise direction. So in any moment in anti-clockwise direction is positive. So now the moment due to this mg about O, it is in the clockwise direction. Therefore it is minus. Therefore it is minus. So minus what? Mg, this is the force, multiplied by what is the perpendicular distance? Just extend this line. So do you agree that this is the perpendicular distance between the two? This is the force and this is the point, and this is the perpendicular distance, or you can extend it here, and you know that this is your perpendicular distance. So what is this distance? So from here to here, what is this length? This is here. And if this is sine theta is equal to this divided by L, and this is what I want, and this is multiplied by L sine theta. This is the perpendicular distance between the force and the point. E is equal to, okay, I is the moment of inertia. So moment of inertia about the point about which the rotation is taking place. So this is the mass, this is the only mass which I have. This string is not having any mass, this is the only mass. And what is the moment of inertia of this point mass about this? So that is nothing but m into L square. That is nothing but m into L square, any point mass. If you have a point mass, okay, so I have m. So I want to find out the moment of inertia of this about point A. So I would like to find out what is IA. What is that? That is nothing but mass multiplied by what is the distance between this and this. So if this is x1, then m into x1 square. I don't want about this. I have another point, say point B. I want to know what is IB. IB is nothing but find out what is the distance between B and M. What is that? If this is x2, then IB is equal to m into x2 square. So like that, moment of inertia of a point mass. Moment of inertia of a point mass. Please remember, of a point mass, what I have here, that is nothing but the mass multiplied by the distance between the mass and the point about which the moment of inertia is required. So here m multiplied by this distance, which is L. So what I require is ml square, and ml square is nothing but IO, the moment of inertia of this point mass about point O. ml square, this is I. And what is alpha? Alpha is nothing but theta double dot. Okay, so I shall rewrite it. That is nothing but ml square theta double dot plus mgl sin theta is equal to 0. So therefore I can cancel m and m, this 0 in it. So now I can cancel one m, so l and it is l square. What is remaining now? It is l theta double dot plus g sin theta is equal to 0. So now we are going to simplify this under one assumption. That what is that assumption? So when this is oscillating now, this is the equilibrium position, and the extreme position of this mass is somewhere here, and from here to here is what this is called as amplitude. The maximum displacement on any one side of the mean position is called as amplitude. We assume that amplitude is very small. Okay, assume for very small amplitude, for very small amplitude. So this is same as for small theta. The value of theta is very small. For small theta, we all know that sin theta tends to theta. Small theta, okay, sin theta tends to theta. So from this, how do we get this? Limit of sin theta divided by theta as theta tends to 0 is equal to what? Is not equal to 0, is equal to 1. Okay, this is same as limit of sin theta as theta tends to 0, this theta into this is equal to 1 into theta. This theta I shall take it to this side. Okay, limit of sin theta as theta tends to 0 is 1 into theta, that is nothing but theta. This is what I have written. So many times we come to the we make a mistake and say that as sin theta, okay, limit of sin theta as theta tends to 0 is not 0, it is equal to theta. Okay, make use of this. Okay, therefore sin theta, and under this condition for very small amplitude, for small theta, I shall rewrite the equation. What is that? L theta double dot plus g into theta. This is equal to 0. So again I would like to make the coefficient of this theta double dot as 1. Theta double dot plus g by L into theta is equal to 0. Go back to this. So we had a very similar x double dot plus omega square x is equal to 0. So here x has been replaced by theta, nothing else, and therefore I don't have to. Okay, this is a differential equation which indicates the motion of this, and the solution of this is simple harmonic. The solution of this is simple harmonic whose frequency is omega n is equal to root of g by L. Therefore, the natural frequency of simple pendulum is root of g by L. I hope you have understood. Okay, probably you have studied this, you have written it in your school days also, and probably straight away you have written, and without analysis you might have written it. I hope you understand, and therefore, so I shall rub this all this, and straight away write what is the equation? The equation is theta double dot plus g by L into theta is equal to 0, and therefore omega n is equal to root of g by L. So this is what we have done. By what method we have done it? Please remember, we have employed Newton's second law, nothing else. Now the same problems I would like to do it by what is called as the D'Alembert's principle. Okay, we may spend some time, few minutes on understanding what is meant by D'Alembert's principle, but once we understand it, the method is almost very same as Newton's second law. That's why I said, please remember, understand whether you are applying this or whether you are applying this. There is a very thin line of difference between the two. D'Alembert's principle. Okay. I don't know whether you have heard it or not earlier. Okay, D'Alembert's principle, what does it do? How does it help? It helps us to apply equilibrium conditions for a moving body. Okay, something very contradictory statement like, okay, when can I apply equilibrium conditions? I can apply equilibrium conditions if the body is in a equilibrium state. That is, if it is stationary or if it is moving but its acceleration is zero. If the body is having zero acceleration or if it is stationary, then I say that the body is in a equilibrium state. And what are the equilibrium conditions? The resultant force is zero, the sum of all the forces equal to zero, and moment due to all the forces about any point, that also is equal to zero. These are equilibrium conditions. So I can apply equilibrium conditions only if the body is stationary. So most of our problems are going to be that, stationary. But if the body is moving, that too with certain acceleration, the body is moving with certain acceleration, then can I apply equilibrium conditions? I cannot apply equilibrium conditions. But if I make a small modification using this principle, D'Alembert's principle, then still I can apply equilibrium conditions. Okay, that is what is called as D'Alembert's principle. So what is that small modification, that we shall understand. Okay, so imagine a body, and say its mass is m, and say g is the center of gravity of this body, and say its I suffix g is the moment of inertia of this body about g. G is the center of gravity. I hope you understand what it means, the difference between centroid, center of gravity, etc. You all know. Okay, so anyway, it is subjected to a number of forces, say all planar forces. The forces are restricted to one plane. Say it is subjected to AF1, it is subjected to AF2, AF3, like that. A number of forces. Say I have applied a number of forces on this body. Okay, so you can imagine some angle here, direction, some values. Okay, so if I give the values, probably then you will be able to tell whether it will move or not. Okay, I have applied all these forces. Then what may happen? What are the different possibilities? Please, this is what we call it as a flow chart like analysis. Okay, these are the forces I have applied. What may happen? What are the different possibilities? The body may not move. This is one possibility. The body may not move. Why? Because all these forces are in such a way that they follow equilibrium conditions, and hence there is no question of resultant, and the net moment also is zero. The body is not moving. That is one possibility. Okay, so I don't want that. I assume that if it is in equilibrium condition, there is no question of applying D'Alembert's principle. The second possibility, okay, what is the second possibility? The body is in motion. Okay, the body is in motion. Okay, fine. When the body is in motion, it is a planar only. It is restricted. The motion is restricted to one plane only. What kind of motion? The possibility is it may be moving along a straight line, say horizontally or vertically or in any inclined direction. That is possible. Okay, so one possibility is it is going to move only along a straight line. That also is a possibility. And the other possibility is the body is rotating. It is not moving along a straight line. It is undergoing a pure rotation. The forces are such that if the whole body is rotating and it is having angular acceleration. If the body is moving along a straight line, it is having linear acceleration. If its body is rotating, then I have angular acceleration. And the third possibility, what is that? The body is moving along the straight line and also it is undergoing rotation. That is a general one. Okay, that will cover all the cases. The body is moving along a straight line and also having acceleration, angular acceleration. It is rotating and it is moving along a straight line. So that I shall indicate it. So just for the convenience, I shall assume that it is having linear acceleration in the horizontal direction. Say AG. A suffix G is the acceleration. And let me assume that it is also rotating with an angular acceleration alpha. So what happens now? It is moving like this and simultaneously it is rotating. Please remember here. So when I draw it something like this AG is maybe somewhere here. That means it is rotating. It is moving along the straight line. The whole thing is remember this. Okay. When it starts moving, it is rotating and also moving like this. I hope you understand. So this is a general case. If alpha is 0, it is moving along only this thing. If AG is 0, then it is undergoing only rotation. If AG is 0, alpha is 0, that is in equilibrium state. So that means if I take this case, that will cover all the previous cases, depending upon what are the values of AG and alpha. So since it is having the motion, I cannot apply equilibrium conditions. Okay, I cannot apply equilibrium conditions. But I would like to apply in a sense, not apply, I want to imagine certain force and certain moment and bring this body to stationary mentally. In my mental this thing, I would like to bring it to stationary. So for that, see, as you know that it is actually moving along this line, straight line. So I want to imagine a force on this and so that it is not moving. So what should I do? So I shall imagine a force. Please remember, it is only an imaginary force. Okay, so what is that force? That force is equal to M into AG. So this M into AG is a force which is responsible for the motion of this in this direction. I imagine an exactly opposite force. So M into AG, a force opposite to acceleration. This is what we call it as inertia force. And similarly, okay, now it is not going to, with this force, it is not moving along the straight line. But there is something which is rotating and I apply a couple moment opposite to this alpha. So how much is that? That is equal to I or Ig multiplied by alpha, or in general I shall call it as I into alpha. If I apply I into alpha, then even the rotation is not taking place. Then all these forces F1, F2, F3, F4, F5 and this M into Ag, the sum of all this or the resultant of all this must be 0. Because it is not moving, it is having stationary now and I can apply equilibrium conditions. And similarly, the moment due to all these forces about G, including this I into alpha, that also must be 0. Okay? So any body which is moving with certain acceleration, then that can be imagined to be stationary by applying an inertia force and inertia moment and then apply equilibrium conditions. Okay, that is the statement, that is the principle of D'Alembert's principle. D'Alembert's principle helps us to apply equilibrium conditions for a moving body. I hope you understand. Okay, now it is very very simple. I take hardly 2 or 3 minutes to complete this. Okay, now for example, the spring mass system. I shall straight away take this, the last question, that is this M. Okay, what are the forces that are acting? I know that mg, which is acting this thing. Then I know that it is moving, it has undergone a displacement x, it is having velocity x dot, it is having the acceleration x double dot in the downward direction. Then I know that the spring is pulling it up, and what is the force? K into delta st plus x. Okay, under these forces it is moving. I don't want it to move. I don't want it to move, and therefore I imagine an inertia force. So what is the magnitude of the inertia force? M into E, M into mass into acceleration. M is mass. What is acceleration? X double dot. M into x double dot is the magnitude of the inertia force. How should it act? It should act opposite to acceleration. X double dot is imagined to be downwards, and therefore I imagine a force in the upward direction. What is that? M into x double dot. Please remember, this force was not there. I have imagined it. What is this inertia force? Under the action of this, now it comes to rest. I can apply equilibrium conditions. Apply equilibrium conditions, sum of all the forces equal to 0. That is nothing but K into delta st plus x plus M into x double dot minus mg is equal to 0. Okay, expand this. K into delta st plus K into x plus M into x double dot minus mg is equal to 0. So I know that K delta st and mg, they are one and the same. So if you draw the free body diagram here, mg is the force, K delta st is the upward force. So this is same as M x double dot plus K into x equal to 0, or x double dot plus K upon M into x equal to 0, and therefore omega n is root of K by M. Now this method is D'Alembert's principal method. I hope you understand. Delta st. This is delta st. I hope it's clear. Okay, so now similarly, very similar. So it's just 1 minute more. Okay, for simple pendulum, straight away I go to this. This is my point O, this is the mass. So I know that this is mg, and this distance, displacement is theta, and this is theta dot and theta double dot. Okay, this is mg, and I know that this is tension T. Okay, so I have to apply a torque. I have to apply an inertia torque. Okay, how is that inertia torque? Opposite to angular acceleration. Theta double dot is anti-clockwise. Theta, okay, the inertia torque is in the clockwise direction. How much is that? That is I-O into theta double dot. Okay, sum of moments about point O equal to 0. This I-O theta double dot is in what direction? Is in, okay, I-O theta double dot. This is my clockwise direction. Okay, so anyway, this T will not get me any moment. Then mg, this also is clockwise. Therefore, plus mg into L sin theta is equal to 0. So I-O is nothing but ml square theta double dot plus mg L. For small theta, sin theta becomes theta. This is equal to 0. So simplify that. So you will have theta double dot plus g by L into theta equal to 0. Therefore, omega n is equal to root of g by L. The same thing. Okay, so it's very difficult to know whether we are applying D'Alembert's principal law or Newton's second law. But if you imagine this, then only it will be there. It is D'Alembert's principle. If this is not there, then I know that it is moving. Then I shall apply what is called as m is equal to I into alpha, or in that case f is equal to ma. If I apply that Newton's second law, okay, the same thing. And maybe in my next class I shall explain you what is meant by how I can employ energy method for the same problem. Okay, we shall stop now.